I'm going to go ahead and do this circular motion 4. This is about orbital motion. You should have your notes handy and have those. There's a few new equations that we have that we're going to need. Those are this, the velocity of something that's in orbit, and this. Okay, so I've got those handy. Suppose you are at mission control on the moon in charge of launching a moon-orbiting communication satellite. How much would a 1,500 kilogram satellite weigh at the surface of the moon? And the gravitational field strength on Earth's moon is this. So this is instead of 10 newtons per kilogram here on Earth. When we want to figure out how much does something weigh, in other words, what's the gravitational force on it, on Earth, you multiply by 10. On the moon, you would multiply by 1.6. Things do not weigh as much on the moon. So, of course, the mass is the same. So 1,500 times, instead of multiplying by 10, I would multiply by 1.6. Every planet, moon, whatever, would have its own different number depending on how massive it is and how big it is, how the radius of it. So that's about 2,400 newtons. Now this satellite on the Earth would be 15,000 newtons, right? When the satellite is in orbit, how big will the centripetal force be? It will be less than 2,400 newtons because, like, this is what it is at the surface of the moon. So when it's up in orbit, it's going to be because the R is greater. If you get further away from that surface, then it's going to decrease. And how do we know that? Because universal gravitational force, the further you get away from that planet or sun or whatever it is you're orbiting, the smaller the gravitational force will be. All right. The satellite is to have an altitude of 1,000 kilometers. Right off the bat here, then an alarm bell should go off here, not the right units. We need everything to be in meters, seconds, kilograms. So 100 kilometers, kilo means 1,000. This is the same as 100,000 meters. Above the moon's surface. What is the radius of the orbit of the satellite? And then a little information for you here. The radius of the moon is about 1.74 times 10 to the 6 meters. So we're going to have to do that, this little calculation in a lot of these problems. Here's the moon, and the radius of the moon is this, and then the satellite is out here. This is the radius of the moon. This is the altitude, right, above the moon's surface. So if you want to know the actual radius of the circle that satellite is moving in, it's just this plus this. The radius of orbit is just equal to the radius of the moon right here plus the altitude. That's not an equation I'm going to give you because it's just an obvious fact once you draw the picture. So radius of the moon is 1.74 times 10 to the 6, and the altitude is this, which is 10 to the 5th, and you can do that in your calculator or realize that that's this decimal place. That's 1.84 times 10 to the 6 meters. Okay, So notice where that difference right here, where that showed up in the decimal places. So what does that mean? It means even in this drawing, which might look like kind of a low orbit to you, it's actually much more like this. Like when we put things into low orbit around the Earth, the Moon, whatever, it's really quite close to the surface of that thing. Like when you look at images from the International Space Station, which are obviously faked because the Earth is flat. Just kidding, they're not. The astronauts there cannot see. They're not like way out here looking at the Earth. They're like right here looking at the Earth. So like it's a pretty stunning view from way up there, but they're pretty close. Like they can't see all the way, like from side to side, for example. All right. Find the required orbital velocity of the satellite. So that is my equation. V is equal to the square root of g of the mass of whatever the thing is in the center over r. Right. And the mass of the thing in the center, if you're thinking to yourself, I should have included this right here. If you're thinking to yourself, oh, wait a minute, what's the mass of the Earth? You do need to know that to do this because, oh, wait, the orbital, oh, just kidding. The thing in the center here is the Moon, right? I was thinking about the Moon going around the Earth. So I lied. What you need to know is the mass. Oh, we need to know what the mass of the Moon is, which I also didn't give you. Dang it. I think that is missing, so we need that. Mass of the Moon. These things will be given to you. I don't know if I remember what the mass of the Moon is. I think I'm going to have to grab my phone and look that up. Let me just set up this calculation. So that is, I'm just going to leave this as a G because I have it stored in my calculator. And I know what the R is, right? I found that here. And then I just need the mass of the Moon here. Hold on 1 sec. All right, I'm coming back. Hey Siri, what is the mass of the Moon?
The Moon is Earth's only proper natural satellite. At 1/4 the diameter of Earth, it is the largest natural satellite in the solar system relative to the size of its planet, and the 5th largest satellite in the solar system overall. Would you like to hear more?
Yes.
Orbiting Earth at an average lunar distance of 384,400 kilometers, or about 30 times Earth's diameter, its gravitational influence is the main driver of Earth's tides and slightly lengthens Earth's day.
Just tell me the mass already. It's coming. Here we go. Distance. Surface gravity is about 1/6 of Earth's, which we saw. You can see there. I guess nobody cares. Why is the... There we go. There it is. So about 7.3 times 10 to the 22nd. Mass of the Moon is about 7.3 times 10 to the 22 kilograms. Okay, there we go. Needed that. 7.3 times 10 to the 22. I'm not going to put my units in these calculations. Okay, so I am not going to be the person who just hits enter all the time on my calculator. I'm going to enter an expression that looks just like this so I can see that I did it right. Square root, and inside my square root sign I want a fraction, so I'm going to go alpha F1 and bring up that fraction thing. And then I'm going to get my G, right, because I stored it in there. times 7.3, use the little exponent entry thing, 22, and then on the bottom, 1.84 times 10 to the 6. I think that looks good. All right. If I do all of that right, this is, remember, what are we finding here? This is, I used 2 sig figs here, so I think I'm just going to round that to 2 sig figs. That's good enough. This is the orbital speed of our satellite. And since we did SI units here, that comes out in SI units. Great. How long will it take the satellite to orbit the moon? How long does it take? There's 2 ways that we could do this. Now, since I already know this, I could just use this equation. Right, I can do algebra and just swap those. That would be the easier way to do it. You could also do this. I'll do it this harder way. So here, if I want to solve this for t, t would be equal to the square root of all of this. 4 pi squared over g, whatever mass of the thing in the center, times r cubed. All of that under the square root sign. All right, so I'll do it that way. I'll pretend I didn't see the easier way to do it. So I need another square root sign. Underneath that, I need another fraction. And then under that fraction, I need 4 pi squared up top. And I need g times the mass of the thing in the center, which I have here. That's 7. I like to have a little time sign. I think the calculator does okay there without the time sign in between these, but it doesn't look good to me. Freaks me out. All right, so I think we're looking good. We're trying to do this, right? So I got 4 pi squared over g times the mass of the thing in the center, and then times the radius cubed, and the r is this, 1.84 times 10 to the 6, and then I need to cube that, so I like to put that in parentheses, and then cube that. All right. And I mean, look, come on, that looks so nice compared to like the hitting enter, hitting enter, hitting enter kind of thing. So how long will it take? 7,100 seconds. And there's 3,600 seconds in an hour. So that's about 2 hours, which is typical of low satellite orbits. The International Space Station, I think, takes about 90 minutes to go around the Earth. Is this satellite accelerating while in orbit? If so, what is the direction and the magnitude? Yes, because it's moving in a circle. So the direction is toward the center. And the what is the direction of it? Well, I know that centripetal what's the magnitude of it? I know that centripetal acceleration is equal to v squared over r, right? That's one of my circular motion equations. So here that's going to be v squared over the radius of the orbit as this. So I'll just pop that into the calculator. Squared divided by 1.84 times 10 to the 6. So that acceleration is about 1.4 meters per second squared for the moon to move in that circle. All right, so there's a lot of calculator management in these problems. That's just the way it is, folks. Why do astronauts float aboard the International Space Station? So this is kind of a little bit of a tricky question here. The one way to understand what orbital motion is, it's kind of like there's something that's like falling toward the Earth, like this, like in the same way that, you know, if you launch something here, it would do that. But it's falling just at the right speed, so it just keeps missing, right? It's falling this way, and it's kind of arcing this way, but no, it missed, and it's just keeps going around. So in exactly the same way, like if you were in an elevator and the cable snapped and the elevator started free falling, you would feel weightless. You would like float inside that elevator. Why would you feel like you're floating? Because you're falling at exactly the same rate that the elevator is. So relative to the box around you, you feel like you're weightless because you're falling and it's also falling. So that's what's happening inside that International Space Station. Well, it's probably fun to be on the International Space Station, but there's no unbalanced force on them because they have the same motion as the International Space Station. So what sensation does an astronaut feel while in orbit? They feel weightless. But is there any gravity on them? Yeah, of course there is. There's that gravity toward the center that's moving them in a circle, just as the International Space Station is also moving in a circle around the Earth. Are they really weightless? No. What might be a better description? We could say that they're experiencing, and it's actually called this, apparent weightlessness. And how do you train astronauts for this? Well, you take them up in a plane and you fly that plane in a parabolic arc that simulates or follows exactly the same trajectory that a projectile would, like if you just like hurled something through the air. And then if they're on that exactly in the same way as this, just like the elevator, they will feel weightless. There are videos, cool videos on YouTube of that. There's some like music video. I don't know what the song is. There's a music video where the people in the band, I guess, are like on an airplane that keeps doing that, and like so they're like sitting there in the airplane, and then it starts to do one of these arcs, and they start floating around, and then it stops, and you should check that out. It's pretty cool. And of course, those people on that airplane are not weightless. It's just that the airplane is flying in a trajectory that is simulating a free fall. So that's probably not typical of a question I'm going to ask you on the test. I'm going to make you do some of this math. Space Shuttle aims for an orbit about 250 kilometers above the Earth's surface. So that is 250,000 meters, and that is the altitude, not the radius of the orbit. In orbit, the mass of the space shuttle is this. The radius of the Earth is this, which is, that's wrong units again, that would be 6.38 times 10 to the 6 meters. Calculate the orbital speed of the space shuttle. So to do that, I would need either one of those. So let's see which one we have. To do this, I would need the, this is g times the mass of the thing in the center, not the space shuttle, over r. Or I would need to do 2 pi times the radius times the time of the orbit. And I don't think it told me the time here, so that's not going to work. I am going to need to know the mass of the Earth here. And I should have included that. Mass of Earth. I'll put those things in the assignment in Google Classroom. That's what I'll do. In orbit, the mass. So sorry, just talking to myself. The mass of the Earth is, let's see, I remember this. Is it, I think it's about 6 times, yeah, that's what it is. It's about 6 times 10 to the 24 kilograms. GM, mass of the Earth, is equal to 6 times 10 to 24 kilograms. And the radius of the orbit, well, the radius of the orbit is the altitude of the orbit plus the radius of the Earth, right? Because there's the planet, there's the space shuttle. So I need to do this plus that. Okay, so the altitude is 250,000, and the radius of the Earth is 6 point, there it is in the right units, times 10 to the 6. And that's going to be 6 point, let's see, 6.63 times 10 to the 6 meters. The 25 falls on those decimal places there. All right, so let's try to do that. Square root, we're going to make my big fraction. There we go, there it is. I got my G stored. If you're wondering, does it keep track of the G after you turn the calculator off? Yes, it does. If you have any programs you use on your calculator, then it's possible that the program could change the value of G if it uses that in the code of the program, if it uses the letter G. You can always just check by just typing the letter G and hitting enter and see if it's there. Definitely would want to do that before you took like a test or something. Okay, I think that's good. So I've got G, there's the mass of the Earth, radius of the orbit. So that's about, what would we want to call that? About 7,800 if we're going to do 2 sig figs. This is the velocity, so that's in meters per second. That's how fast the space shuttle is going. Calculate the orbital period. 2 ways to do it. You can use the Kepler's third law equation, or you can use this, because I now know what the radius is in the V. So I'm going to do that. I know that V is equal to 2 pi r over t. Algebra, t is equal to 2 pi r over V. So that is going to be a little bit easier to manage in my calculator. 6.63 times 10 to the 6 over the V is 7,800. Get my fraction there. I got 2 pi times 6.63 times 10 to the 6 over 7,800. So that's about, I'm going to call that 5,300. This is the period. That's an amount of time going to come out in seconds. If you want to know how many hours that is, divide that by 3,600. That's about 1.5 hours. Right? That's right where the space station. Didn't I say that it takes about 1.5 hours for the space station? There you go. All right. Back in Galileo's day, one of the objections to the heliocentric model is that if the Earth's spinning, why don't all the people just go flying off? Which, you know, I don't know. I guess that's kind of reasonable. It turns out it's pretty dumb. after you do the physics. Actually, you do weigh a bit less on the equator. So how much, do a force diagram for a 100 kilogram person standing at the equator and at the pole, and do the unbalanced force calculations. So I'll show you why we don't go flying off. So if this is the equator, and if we got a 100 kilogram person going around like this in a circle, then there must be unbalanced force toward the center of the circle. And we know that the force toward the center, that's the force of gravity on them, right? And we also know that there would be a support force. So the question is, like, what would the difference between those have to be? Well, if this person is moving in a circle, then I know that the unbalanced force on them must be, well, here, let me just write this too. Unbalanced force would be equal to here. That's winning toward the center of the circle. The support force on them is losing. And I know that if it's a 100 kilogram person, that multiplied by 10, that's 1,000 newtons. And I know that unbalanced force is equal to mv squared over r. Okay, so do I know how fast they're going? Well, v is equal to 2 pi r over t, and the radius of the Earth is 6.38 times 10 to the 6 meters. And I know that the amount of time it takes to go around is 1 day. And if I convert 1 day into seconds, because everything has to be in meters and seconds and kilograms. So if I convert that, that's 86,400 seconds in 1 day. That's how long it takes them to go around their circle. So how fast is that person going? They are going 2 pi times 6.38 times 10 to the 6 over 86,400. So about 464 meters per second. Okay, seriously, they'd go flying off, right? Well, hold on a second. So if we figure out how much unbalanced force then, mass of the person is 100, not 1,000. That's the gravitational force. 100 times their velocity squared, and then divided by the radius, and it's a pretty big circle they're moving in here, right? And let me get my fraction thing up here. 100 times 464 squared divided by 6.38 times 10 to the 6. Oops. Dang it. Forgot what I was doing there. 6.38 is 10 to the 6. How's that look? Good. That's about 3.4 newtons. So here, I know that unbalanced force is equal to force of gravity winning toward the center, normal force is losing. So 3.4 is the unbalanced force. Force of gravity on them is 1,000 minus the normal force. So the force of support on them, which is how heavy you feel, right, is 3.4 newtons less. So that's 996.6 newtons. So are you a little bit lighter because of the circle you're moving in? Yes, but not much. This is called the equator diet. You go to the equator and you weigh a tiny bit less. Now, what about if you're standing up here at the North Pole? Well, if you're standing at the North Pole, you're not actually moving in a circle because you're right there at the pole. You're like very slowly rotating around yourself, like once every 24 hours, but you're not moving in this fast circle. You don't have any velocity like this. You're just standing there. So there, how much is the normal force on you there? Well, the forces are balanced there. So it would just be, 1,000 newtons. So do you feel slightly less at the equator? Yeah, you do. There you go. And last question. The Earth's orbit around the Sun is very nearly circular, with an average radius of this. That's 1.5 times 10 to the 11th meters. That came up in the notes. And the mass of the Earth is this. Determine the average speed of the Earth in its orbit around the Sun. Okay. I don't need to add the radius of the Sun here because we are so far away from the Sun that that doesn't make any difference. So that makes things a little bit easier for us. So average speed of the Earth in its orbit around the Sun. I know that speed is equal to 2 pi r over period. I could do that. Do I know the r and do I know the period? Yes. I know this distance and I know what the period is because I'm an Earthling, and so I know how long it takes for the Earth to go around the Sun. It takes a year. That's why we have seasons and stuff. So 2 pi times the radius, 1.5 times 10 to the 11th, divided by the period, which is how many seconds there are in a year. That is, I've got 365 days times 24 hours in a day times 60 minutes in an hour times 60 seconds. That's about 3.15 times 10 to the 7th. All right, so how fast is the Earth going around the Sun? Going to bring up my fraction here. 2 pi times 1.5 is 10 to the 11th over 3.15 times 10 to the 7th. So about, I'm going to run that up to 30,000. 30,000 meters per second. So hold on tight, folks. That is how fast the Earth is going around the Sun. So why don't we all fly off? Well, we kind of went over that here. The thing is, the circle is so big that as we like cruise around this big circle around the Sun, it really is like almost straight. So the amount of acceleration toward the center is tiny, tiny, tiny. And like, why don't you feel like some crazy wind or something from going this fast? Well, there's this thing called the atmosphere around the Earth. Probably you've heard of it. And the atmosphere is like stuck to the Earth because of Earth's gravity, and it's moving with the Earth. So, you know, we feel wind and stuff from our weather patterns, but we don't feel it from like cruising around at this speed. It's kind of crazy, but we don't notice that at all. What is the magnitude of the Earth's average acceleration? Acceleration for something moving in a circle is v squared over r. There's the v. Here's the r. .006 meters per second squared. So that should give you some idea of how much acceleration is there toward the center of the circle. It is such a big circle that that acceleration is really small, and that's why we don't feel anything. The thing that we experience, if you think about like driving in a car, or here, even better, flying in an airplane at like over 500 miles an hour, and you're just sitting there like reading your book or playing a video game or whatever. It's not like some terrifying experience. Now the takeoff and landing is a little scarier. Why? Because that's when you're experiencing acceleration. Once the plane reaches that constant velocity, cruising speed, you might as well be like, you know, sitting in a room somewhere. So the thing that the human body responds to is not speed, it's acceleration. And this is so small that that's why we don't notice. Determine the gravitational force on the Earth by the sun. How does the force on the Earth by the sun compare to the force on the sun by the Earth? So universal gravitational force is G, and mass of the Earth times the mass of the sun divided by the distance between them squared. You're going to need to know the mass of the sun for this. I think I put that in Google Classroom for you. And I might have mentioned it somewhere else too. So I've got G times the mass of the Earth, which is about 6 times 10 to the 24, times the mass of the sun, which is about 2 times 10 to the 30, divided by the distance between them, which is 1.5 times 10 to the 11th squared. So that's about 3.6 times 10 to the 22nd newtons. Notice that because multiplication is commutative, the force of the Earth on the sun and the sun on the Earth is the same because they both show up in this calculation. But of course that makes sense because Newton's third law, right? The force of the Earth on the sun must be the same as the force of the sun on the Earth. If you're wondering to yourself, wait a second, then how come the sun isn't orbiting us? Maybe Copernicus was wrong. Well, the reason that we're going around the sun is way more massive than we are, right? So the sun is kind of like anchored there, and we are going around it because the gravitational force of the Earth on the sun is not enough to get it moving into a big circle. It is enough to make it wobble a little bit, and if you care about things like this, how do we look for planets, like exoplanets, out there in the universe around other stars that are very far away? We can't actually see those planets because, I mean, we can just barely see those stars, right? So how do we know, how do we determine when a sun has a planet? There's a couple of ways. One is to have very, very sensitive instruments that detect like a very small change in the brightness as a planet like transverses across the face of its sun. But another way is to detect like a tiny little wobble back and forth in the motion of the star. If there's a tiny little wobble, that's because something's moving around it and tugging just slightly on it. So like our sun wobbles a tiny bit because of the gravitational pull of the planets going around it. But it's so much bigger that that wobble is very tiny compared to our big circle.